I'm Dr. Roger, and today we're looking at solving systems of first-order linear ordinary differential equations using eigenvalues and eigenvectors, and the emphasis is going to be on sketching the phase portrait at the end. That's a new skill that's well worth developing, and you should be able to do it even without a calculator. Step one is to set determinant of A minus lambda times the identity equals 0. So A is 5/4, 3/4, 3/4, 5/4 minus lambda times 1, 0, 0, 1 equals 5/4 minus lambda, 3/4, 3/4, 5/4 minus lambda. And the determinant is AD minus BC is lambda squared minus 5/2 lambda plus 25 over 16, and then minus 9 over 16 is plus 16 over 16 is plus 1. And we're setting that determinant equal to 0. This factors and if product equals 0, either the first factor is 0, so lambda equals positive 1/2, or the second factor equals 0, so lambda equals positive 2. I'm going to call these lambda 1 and lambda 2. For lambda 1 equals 1/2, if I write A, uppercase A, minus lambda times the identity times vector C equals the 0 vector, that is 5/4 minus 1/2 is 3/4, 3/4, 3/4, and 3/4 times C1, C2 equals the 0 vector. And we notice that this system does not have a unique solution, but that was our goal when we found eigenvalues. If we choose C1 equal 1, then we easily see that C2 is negative 1, so eigenvector 1 is the vector 1, negative 1. Doing the same thing for eigenvalue 2 equals 2. 5/4 minus 2 is negative 3/4. And that times C1, C2 equals the 0 vector. And this is for A minus lambda 2I times C2 equals the 0 vector. And this was A minus lambda 1I. If you choose a value, lambda 1 equals 1, mathematicians will usually say let lambda 1 equal 1, but I like the word choose better here when we're getting used to it. Then lambda 2 is also 1, because for vector 1, 1, negative 3/4 times 1 plus 3/4 times 1 does give us 0. So eigenvector 2 is the vector 1, 1. We saw previously that our general solution is x equals c1 e to the lambda 1 t eigenvector 1 plus c2 e to the lambda 2t times eigenvector 2. So in this case, that gives us x equals c1 e to the 1/2 t times 1, negative 1, plus c2 e to the 2t times 1, 1. Where x is the vector x1, x2. those x1, x2 are my axes here, x1, x2. If I sketch my first eigenvector, the vector 1, -1, that means you go right 1, down 1, right 1, down 1. It's a line with slope -1 passing through the origin, and our eigenvalue is +1/2, which I'm going to draw that as an outward arrow away from the origin, because if C1 is non-zero and C2 is 0, we will get just a point on this vector at t equals 0. And then as t increases, we multiply the vector C1 times 1, -1 times an exponentially increasing coefficient, so we move outward along that vector. And I'll label that as eigenvector 1. If C1 is 0 and C2 is non-zero, then we're on the vector 1, +1, which is a vector with a slope of +1. That's supposed to be a straight line, but close enough. That's eigenvector 2. And this one, the eigenvalue is also positive, so we're moving outward. If both eigenvalues have the same sign, the relative magnitude matters for the trajectories. This one has a larger magnitude, and I'll indicate that with a double arrow going outward. If we have a linear combination where C1 and C2 are both non-zero, both increase exponentially, but the second component here increases much more rapidly. In fact, the ratio of the two, if we treat this as parametric, this component is the 4th power, increases as the 4th power of this one. So we will curve to move more in the direction of eigenvector 2, the one with the larger magnitude. And we seem almost to parallel it over time, although not really. Just we curve to look very close to that. They're actually both increasing, just the eigenvector 2 component increases much more rapidly, and our trajectories end up looking something like this. All trajectories, if you go back in time to -infinity, start at or near the origin and go to +infinity. If you start at any point in the plane, you will continue along the trajectory that passes through that point. This illustrates graphically the behavior of your system over time, and often adds to your intuition about the physical system you're trying to understand. Come back soon for my next video. With math, there's always more.